Let's get started. The next topic is Introduction to ARM architecture. This is our new topic. Today and in the following classes, 2 or 3 classes, we talk about ARM architecture. Now, what is ARM? The ARM stands, there are 2 abbreviations for ARM. If you are talking about processor, it has this abbreviation, Acorn Risk Mission. If you are talking about the company which designs ARM processors and sells ARM processors, sells the licenses, it has another abbreviation called Advanced Risk Mission. So the ARM abbreviation for the processor design stands for Acorn Risk Mission. If you are talking about ARM processor, there ARM stands for Acorn Risk Mission, and the ARM abbreviation for the company that designs and sells the license to use that architecture stands for Advanced Risk Mission. If we are talking about the company which makes the ARM designs, ARM architectures, then in that context, ARM stands for Advanced Risk Mission. And remember, this is one point to keep in mind. ARM is the company which doesn't manufacture any ICs, ARM processor ICs. It only designs the architecture and sells the license to the companies. For example, Texas Instruments has ARM processors, whereas Texas Instruments get the license by paying money to ARM company, and it uses ARM architecture in their processors, in their applications. That's what it is. ARM by itself will not or does not make ICs, semiconductor ICs. It only develops designs and sell the licenses to different companies. They may use these architectures in their applications. For example, Texas is one such company, and there are many other companies. All these companies pay money to this ARM company, and they buy these licenses from that, and they can use these architectures, ARM architectures, in their applications. Next, and ARM cores are designed specifically for embedded systems. ARMs are designed for embedded systems. And what are the needs of embedded systems? The needs of embedded systems can be satisfied only if features of RISC and CISC are considered together for processor design. And in the earlier classes, in the beginning classes of this unit 2, we said there are 2 popular architectures. One is RISC, other one is CISC. And ARM, although ARM represents RISC architecture, Acorn Risk Mission, RISC is present in this. R is for RISC. Although ARM states it is a RISC computer, it is not purely RISC computer, RISC Mission. It has the qualities of RISC as well as CISC to meet the needs of embedded system. That is what is mentioned in this slide. So ARM architecture is not a pure RISC architecture. It has a blend, mix of both RISC and CISC features. So there are good features with RISC and also with CISC. So ARM takes the good features of both and made this architecture. So ARM is not purely, although R stands for RISC, in ARM, it is not purely RISC computer, it is both. It has the qualities of both RISC and CISC. Next, in this table we have features in the left column and benefits to the embedded system in the right column. The feature is high performance. If your ARM processor is having high performance, here we are talking about ARM processor. These are the ARM features, and because of these features, these are the benefits that we get while developing the embedded system or for the embedded system. ARM processors are high performance. High performance means speed. It ensures the system has fast response. Response means how fast it processes the inputs and produce the output. Next, low power consumption. ARM process, they consume very little power. Later we will see the why ARM processors are less power hungry than other microcontrollers. Because in other microcontrollers, all the peripherals, whether they are used or not, all the peripherals are turned on with main power supply. Whereas in ARM, most of the peripherals or almost of the peripherals by default, they are in off state. If you want to use those peripherals, you have to turn them on explicitly. That is how they have, that's how ARM processors have this feature, low power consumption. Makes the system more energy efficient. In the normal microcontrollers, whether you are using those peripherals or not, they are continuously in on state and they continuously draw the power and they are less energy efficient. Whereas ARM, most of the peripherals by default are in off state. Depending on your requirement, you have to turn it on, turn those peripherals on, so that you can save energy and makes the system more energy efficient. Next one is low silicon area. Low silicon area. Why low silicon area? It adopts RISC architecture. At least 70 to 80% of the architecture is RISC. Means it doesn't need complex decoding and controlling. So it the hardware of the ARM is very small in size. Reduce the size and also consumes less power. Smaller size means it also consumes less power. High code density. High code density. What is this high code density? High code density means if you want to accomplish certain task, in one architecture you are using only 10 instructions. In another architecture you are using 50 instructions to do the same task. The first case, the first architecture has this high code density. Means the one instruction does more job compared to the second architecture. Whereas first architecture uses only 20 instructions, second architecture needs 50 instructions to do the same thing. So which is having high code density? The first architecture. The first architecture is having the high code density. There is some problem with camera, right? So high code density means if an instruction does more job on an average, then it has high code density and helps embedded system to have less memory footprint. If you convert that into assembly language or machine code, the first architecture, let's say first architecture has 10 KB of memory program, as 10 KB of program, whereas second architecture where 50 lines are there to accomplish the same task, it occupies, let's say, 50 KB, which is having high code density and which needs less memory, program memory. The first case, the architecture in which we have only 10 instructions, and if you convert those 10 instructions into machine language, we have got 10 KB. We need only 10 KB of memory, program memory. And how this ARM achieves this high code density? Because of this. Later we will see in more detail. For now, you consider this. Every instruction can be conditional. When we talk about instruction set, there we will see this. Every instruction can be conditional, means you can check condition with the instruction. Most instruction can increment or decrement the value of registers, and most instructions can optionally update the processor flags. This feature is present with instructions. That's why ARM has this high code density feature. If you have high code density, then it doesn't need much program memory. The next feature is load store architecture. Just we have already said this load store architecture. Load instruction is used to copy the data from memory to registers, whereas store instruction is used to copy data from registers to memory. These are the only instructions. These are the only two instructions which can access the memory and no other instruction. All other instructions, they make use of the registers present within the processor. Use it to load data from memory to the ARM CPU register or store the data from the CPU register to the memory, enables the memory access when required. Next, register bank with large number of working registers. And ARM has so many registers in the CPU, within the CPU. If that is the case, you can work faster and required to perform most of the operations within CPU. You don't need to access the memory that often, like CISC architecture do, and provides faster context switch in a multitasking applications. It is more useful if you are running more applications at the same time, multitasking applications. Otherwise, the system gets slower. Next, now we'll talk about the data flow architecture of the ARM 7. We have chosen ARM 7 because there are many versions, ARM 1, M1, V1, V2, V3 and so on. ARM 7 and higher versions, they have more or less the same architecture. There are differences also. If you understand ARM 7 architecture, that becomes the basis for higher ARM processors. Now let's see, this is the diagram. This is the data flow model of the ARM. And in this you can see, it is not the full diagram, it is partial architecture of the ARM 7. And you may notice it has instruction decode and control in it, address register, incrementer, register bank, MAC, barrel shifter, ALU, data out register, data and register, and also RMRs are given. There are two buses here, A bus and B bus. There is a program counter, and from ALU we have ALU output can be fed to register bank and also to address register depending on our requirement. And this is program counter is connected to incrementer and also to address register and also to register bank. And this is, let's go back to the previous slide. So here we talk about ARM 7 being the basic architecture for higher versions also. If you understand, then it becomes very easy to understand higher architectures. That's why we are dealing with ARM7. ARM7. In the ARM7, we will find these different units within the CPU core: address register, incrementer, register bank, MAC, barrel shifter, ALU, instruction decoder and control unit, data in register, data out register. Just now, what all different blocks present within the CPU are furnished here. Now see, let's talk about this block diagram and its data flow. Data flow means while executing the instruction, how data moves from memory till the execution completes, till the instruction completes its execution. How, in what way it moves, in what way data moves from clock cycle to clock cycle and so on. It is very important in understanding the processor architecture. Let's see. And here we are not showing the memory. We have not shown the memory. Memory is present outside the processor. We are showing only the processor, the two main units. There are many other which are not shown here. You may think memory is beside the processor, and in the memory we have program and also the data for processing, right? And when the instruction is fetched, the instruction gets into the control and instruction decode unit. The very first place, when instruction enters into the CPU, it gets into control and instruction decode unit. In this unit, the instruction decoding takes place, and according to the type of instruction, control signals are generated by the control unit and data path is created. It turns on certain blocks here, it turns off certain blocks depending on the type of instruction. It turns on certain registers and so on. It issues so many control signals. There will be so many control signals coming out of this control unit, which are connected to different parts within the CPU, different blocks within the CPU. Some wires, some signals are connected to barrel shifter, some control signals are connected to MAC, some control signals are connected to ALU. Is it an addition operation? Is it a subtraction operation? Or what type of operation? Depending on that, ALU performs its operation. Like that, here those connections are not shown. If you get into the real architecture, then you will see all those things. And this is, let's understand, this is the control unit. This is where the instruction gets into when it enters the CPU. After entering into this unit, the instruction is decoded and necessary control signals are generated by the control unit. Further, those control signals control the different blocks within the CPU. Control means it turns on certain blocks, it turns off certain blocks, so that a proper data path is created and instruction is executed. And see, one thing here is register bank. What is register bank? Register bank means a group of registers. Register bank here means group of registers. Group of registers. Group of registers. How many registers are there? That we will see later. Totally there are 16 registers or 15 registers, 16. Register bank means group of registers. Means these are the registers present within the CPU, and if you want to add two numbers, they must be the data which is present within the which is, if you want to add two numbers, those numbers are stored in memory, let's say in this memory, but we have to use load instruction to copy the contents of memory to these registers, because ALU can access only these registers. ALU add numbers, subtract numbers, or multiply numbers, or it performs OR operation or subtraction of, or AND operation with the data which is present within the registers present in this register bank. This ALU cannot talk directly to memory which is outside the processor. So register bank has this many registers, 15 registers or 16 registers, and see they from the register bank, these registers are connected to ALU. There is ALU where all the arithmetic and logic operations are done, and this register bank having 15 registers, all these registers are connected to ALU in two paths. One is through A bus, other one is through B bus, like this. The first path is A bus path. All these registers are directly connected to A bus by using A bus, directly connected to ALU by using A bus. All these registers are also connected to ALU in the second path by using second path. Second path is indirect. In the second path, follow this. In the second path, we have a barrel shifter. So when second operand, see if you are performing addition operation, we need two operands. Thus, the first operand comes directly to ALU by using A bus. First operand where it is stored in the register bank, in the registers, in one of the registers. Like we have R0 register, R1 register, R2 register, R3 register, R4 register. Let's say one first operand is present in R4. That R4 data comes to ALU through A bus directly. Whereas second operand necessary needed for addition is present in R5. Let's say R5. R5 that comes like this. It comes through B bus through barrel shifter and reaches the ALU. And in the ALU, that addition is performed. Addition of R4 contents are added with R5 contents. How do you get R5 contents? Through second bus called B bus, and it reaches through barrel shifter, and it reaches the ALU through barrel shifter. Barrel shifter has certain significance. You can shift left or right and so on in the barrel shifter, that too within the same clock duration, within the same clock cycle. You doesn't need separate clock for barrel shifter operations. Within the same clock, you can do both barrel shifting as well as ALU operations. That is one good thing. And see, after adding these two contents, R4 contents and R5 registers, after adding the data present in R4 register and R5 registers, we'll get some result. You can write that result back to one of the registers, let's say R6, and that path is provided, that path is shown here. Output of the ALU has given to register bank, it is also given to address register. This address register, we don't write, we also use address register for other purposes. If you are executing load store instructions, then the address of the memory locations are calculated in the ALU along with barrel shifter. The address is calculated within the ALU, that is sent to address register. And now address register holds the address of the memory location and so on. Generally, address register holds the address of the next instruction or memory location, like that, from where the instruction or data is to be fetched. That address is temporarily stored in the address register. Now that is this. And let's see, there is some now finally the result is stored in which register? Let's say R6 register, and the contents of R6 register is stored back to memory. Let's say we want to store the contents of R6 register in one of the memory location. Now how it is done? R6 are loaded through B bus and reaches the data out register. Data out register is like a buffer register. It holds the contents temporarily. Now R6 contents are stored in data out register, and these contents are written to that memory location. And before this, the memory location should be stored in the address register like this. And see here, if it is instruction that goes to instruction decode and control unit. If it is a data that it goes like this. Actually, there is a path, it is not shown here. From data register, there is a path to register bank. Register bank contains all the registers R0, R1, R2, all those things. And incrementer, what is the need of incrementer? Incrementer, so one instruction is stored in the memory in the location 2000. Next instruction will be stored in the memory location, let's say 2004. Why 2004? Memory is each memory location is having 8 bits, let's say, and the instruction is 32-bit wide. 32-bit wide means the one instruction, current instruction is stored in 2000, where what is the address of the next instruction? 2004. Why 2004? We need 4 memory locations so that we can accommodate 32 bits. So this incrementer does that incrementing job. It keeps on incrementing and makes the address and calculates the address that will be stored in the address register. And there are some cases when you use jump instructions, and according to jump instruction, the address next instruction is not the address of the next instruction will be something else. It is not next instruction, actually it will be something else. Accordingly the address register is updated by program counter, all these things. Program counter or incrementer are one the same. This little bit understanding of this architecture. Let's understand in more detail. The MAC unit means, okay, we have missed it. MAC means M stands for multiplication, multiplication accumulator. MAC stands for multiply and accumulator. Multiply and accumulator means it is a multiplication circuit. And accumulation means, suppose if you are performing some multiplication, you will get some intermediate results. Those intermediate results are stored in the accumulator register of the register bank, and those intermediate results are used in the multiplication process. Like how we multiply two numbers. If you are multiplying two numbers on the paper, we get some intermediate results which are needed, which are necessary. Those will be added to the subsequent numbers that are generated in the multiplication process. Exactly in the same way, this is the multiplier, and it also has accumulator. In those accumulator, intermediate results are stored, which will be used later, which will be used in the following multiplication process. Next, so let's start what we have discussed in the black diagram. Right, the register bank. Now we talk about the register bank, which is this one, register bank. It has how many registers? The register bank has 16 general purpose registers, and they are named like this: R0 through R15, R0, R1, R2, R3, R4, like this up to R15. means totally how many registers we have? 16 registers. And current program status register, and there is one special register called current program status register, which are accessible by user applications. Means if you are writing programs, means user can access this register, CPSR, current program status register. In addition to that, it has 20 number of bank registers specifically used for different operating modes of ARM core. These are invisible to user applications. There are other registers which are visible, which can be accessed or which are used if you are changing the mode of the processor. If mode of the processor is got changed, then accordingly we have other types of registers, and there are 20 other registers. When we talk about modes of ARM, there we talk about these registers. For now we skip this. The register bank has two read ports to read operand 1 and operand 2, and one write port to write back the result of operation to the any register specified in the instructions. And we have seen the block diagram. There we have two paths, input paths for the input ports for the register bank, one output port. It has an additional bidirectional port to update the program counter with address register and incrementer. This can be shown here. There is one port here, there is another port here, right? And these are the two input ports, and these are the two output ports. And through this port we supply register values to ALUs through A bus, first operand. Second operand is supplied to ALU through B bus and via barrel shifter, right? And program counter is also linked with register bank. Means if you want, you can store the contents of program counter to any of these registers. That's what it means. And in this path, we can store the results of the ALU into one of these register bank. How many registers are there? R0, R1, like this up to R15. And there is one special register, CPSR register. That many registers are present here, bank of registers. Next, it has even additional bidirectional port to update the program counter with address register and incrementer. Next, the barrel shifter can shift or rotate operand. Rotate means data, the first data is circulated like this, or shift means the data either moves left side or right side. Rotate means the MSB bit turns into LSB bit and so on. That is what is rotation. The barrel shifter can shift or rotate the operand. Which operand? Operand 2, not the first one, by specified number of bits prior to the arithmetic or logic operations. Before the operations held in ALU, if you want, you can rotate or shift the data present in the second operand. It is a really useful operation that we will see in the instruction set. When we talk about the instructions in the instruction set, there we will discuss these things in a great detail. The 32-bit ALU performs the arithmetic and logic functions. It is ALU is a 32-bit. It performs arithmetic operations like addition, subtraction, like that, and logical operations like and, or. There are so many arithmetic and logic operations. We have the data in and data out registers hold the input and output data from and to the memory. If you are transferring data from memory to registers, then those the data comes to which register? Data in register. Data in register. If you are storing data from register to memory, then it initially gets into data out register. From there it moves to memory location. These are buffer registers. The instruction decoder and associated control logic generates appropriate control signals for the data path after decoding the fetched instruction. If you fetch the instruction that gets into the control unit, there decoding takes place and necessary control signals are generated, and this control unit provides data path for the instructions to execute. Next, the MAC unit is to multiply two register operands and accumulate with another register holding the partial sum of the products. This MAC unit has one accumulator register and multiplier circuit which multiplies two operands. Those two operands will come from the register bank. So if there are two datas to be multiplied in let's say R5 register and R6 register, let's see here. See MAC unit produces multiplication or does multiplication. The first operand is this one, second operand may be this, second operand is this one, and within the MAC multiplication is done, and results may go like this or like this. Okay, MAC generally performs multiplication. It has its own accumulator inside it. So this one is completed. Next one is the encoded instruction byte of the program. The encoded instruction byte of the program saved in the code memory is fetched through data bus, and first it enters into the data in register of the ARM architecture, from where it delivers to instruction decoder. So the first, as soon as the instruction gets into the CPU, it will be stored temporarily in the data in register. From there it moves into instruction decoder, and later on things will happen like this. See, the instruction enters, as soon as it enters into the CPU, it temporarily stores in data in register, and from there it moves into instruction decode and control unit. Next, the required registers are activated in the register bank, and the operands flow out from the two read ports of the register bank to ALU. Operand 1 through A bus and operand 2 through B bus after processing at barrel shifter. The result of operation at ALU is written back to the resultant register through a write port at register bank. This is shown earlier. For load store instructions, after decoding the instruction, the data memory address is first calculated at ALU as specified instruction, and the pointer register is updated at the register bank. The address in the pointer register is given to the address register to access memory and transfer data. While executing these load store instructions, we use both barrel shifter and also ALU to execute these load store instructions. When we talk about instruction set, there we see how barrel shifter and the ALU together calculates the addresses, and those addresses are stored in the address register. Next, coming to the registers. Just now we talked about register bank, and that register bank contains these registers: R0, R1, R2, R3, R4, R5, R6, R7, R8, R9, R10, R11, R12, and R13, R14, R15. They are shaded. It has a additional special purpose. R13 is also called SP register. R14 is also called LR register. R15 is PC. Here SP means stack pointer. R13 additional duty is stack pointer. R14 serves as link register. R15 is program counter and current program status register. These are the registers present in the register bank of ARM7. R7. ARM processor has 16 number of general purpose registers R0 to R15 and current program status register defined for use for user mode of operation. Next, see, each of these registers is of 32 bits. Each of these registers is of 32 bits. If our architecture is 32-bit architecture, then all the registers will be 32-bit wide. Of course, ARM7 is 32-bit architecture, so each of those registers are 32-bit in size. Out of these registers, R13, R14, R15 have special purpose, as we said in this diagram. So R13 is used as stack pointer. What is the use of stack pointer? That holds the address of the top of the stack. Stack pointer, this register is used to store the address of the top of the stack. Okay, stack is you know what stack is. So address of the top of the stack is stored in the stack pointer register. R14 register is what? Link register. What is the use of link register? See, link register that saves the content of program counter on control transfer due to occurrence of exceptions or using branch instructions in the program. Let's say we are right now in the fifth instruction, and the fifth instruction is jump instruction. Means you jump to 25th instruction, let's say. Now after see, when you jump to 25th instruction, after executing the instructions there, you have to come back to 5th instruction. How do you know to which instruction you have to come back? That address is stored in the link register. R14 is the link register used to link the register that saves the content of the program counter. So current instruction or next instruction next instruction address is temporal is stored in program counter. So program counter address is loaded into link register, and when this happens, whenever exception handles, exception means interrupts like that, or if you are executing jump instructions. So when you are using jump instructions, execution moves to some other location. After executing the instructions there, it has to come back to the current or next instruction, right? So how processor knows it? By storing the next instruction in the link register. Okay, after coming back from the jump processing, jump instruction processing, from where it continue to execute the instructions, that address is stored in link register. So R15 is used as the program counter. Program counter, what it does, it stores the address of the next instruction. Program counter that points to the next instruction to be executed. So in the next class we will continue with ARM architecture.